This is the first chapter of chemistry. To start with, let's look at the questions on the screen. The first question asks about how objects around us are related to the study of chemistry. If you have a pen in your hand, the plastic casing was created by a chemist before the plastic went to a factory. The ink in the pen was also created by a chemist. Everything around us has some relation to chemistry. The second question asks how many of our daily activities are related to chemistry in some way. If you cook, you're actually doing chemistry. If you drive or ride in a vehicle to get to school or to get to the store or at home, all of those use an internal combustion engine, which is a chemical reaction. If you eat, the digestion of your food is a series of chemical reactions. Chemistry is around us every day. The definition here is sort of a book definition of chemistry. I think you can probably have one that's a little more straightforward and shorter. You could say chemistry is a study of matter and energy and how they interact. The different types of chemistry are often referred to as branches of chemistry. There are a lot, but the textbook here only really talks about 6. The first one is organic chemistry. When you hear organic, you probably think about going to the grocery store and getting food where it wasn't an artificial chemical pesticide that was used for them. It was something that was natural. In chemistry, organic has a different meaning. Organic really just means that it's in a family of carbon-containing compounds. These are the most abundant compounds we know. About the 13 million different compounds that are known to chemists, about 10 million of them contain carbon and would qualify as being organic compounds. Inorganic chemistry studies pretty much the rest of the compounds. There are even a few of the chemical compounds that have carbon in them that are qualified as inorganic. It's something like carbon dioxide. Inorganic chemistry is very important on an industrial scale. Physical chemistry really studies the energy changes that we experience when we do chemical reactions. Here we have the final 3 branches of chemistry that the textbook discusses. Analytical chemistry is about the analysis of materials, and it's broken down into 2 subcategories. There is qualitative analytical chemistry, where we are looking more at properties of things and identification, and this could be asked, what is it? For the other type of analytical chemistry, it is quantitative, and you can hear the word quantity in there, and so the question then usually becomes how much of something is present or how much of something reacted. Analytical chemistry is the type of chemistry you would see on detective series like CSI. Biochemistry is not only the study of living things and their chemistry, it's also the study of materials that affect living things. Things like medicines, pharmaceuticals, vaccines, which are in the news a lot as I record this because we are in the middle of a COVID-19 pandemic. It also includes things like cloning and gene therapy. Gene therapy is where we can take genetic material from one organism and insert it into another to give the new organism some of the properties and characteristics of the organism that the DNA came from. So you might have a plant that we can insert the genes from a firefly in so that the plant glows. The same thing has been done with goldfish and cats. Spider silk, which is very thin, is also very strong for its thickness, stronger than steel cabling. And so scientists have taken the genetics from a spider and put them into a goat so that the goat's milk also produces spider webs. And so when they milk the goat, they actually can filter away the milk and have a material very much like spider silk. And this is used in medical sutures. Medical sutures are the threads that you would use if someone was injured or having an operation and you needed to sew them up. If the spider silk is used, it can be broken down and absorbed by the body. So if you have a very deep cut, the incision that you're making, you can sew the inside part with spider silk and something more durable for the outside part on your skin. This way, the spider silk is absorbed into your body and processed away, and you don't have to open somebody up to retrieve the silk inside. Theoretical chemistry is all about how the atom works. It's about protons, neutrons, and electrons, and even tinier particles that make up protons and neutrons. It's really about how things work inside of the atom. So it's quantum theory. And so chemicals are just substances that have a definite composition. They've given you a few examples here. Elements also would qualify here, even though they didn't give you any examples as such. This is just a listing of some of the chemicals that you might find if you were making cookies. Basic research is research that people do just for the sake of learning. Something like astronomy or deep sea diving may be considered basic research because they don't have a direct technical or application. Applied research is something you would generally do when you're trying to problem solve. Some of the examples they give here. For basic research, people discovered Teflon. Teflon is used primarily in cookware as a non-stick coating on pans. For the development of new refrigerants, which was a problem when I was a child in the 1980s, the people used refrigerants and aerosols, and some of the materials in these substances would get into the atmosphere and break down ozone. Ozone protects people and organisms from ultraviolet radiation by absorbing it in the atmosphere. As we were using these and they escaped into the atmosphere, these refrigerants would break down the ozone, and so more of the UV radiation, the ultraviolet radiation, came through. So the solution that people came up with, and they actually followed through with this, was that they created a new family of refrigerants. And so today, the refrigerants that you would use in refrigerators and air conditioners are different than what I used when I was a child. And today, the ozone layer is replenishing and doing a better job of protecting us from ultraviolet radiation, largely because we quit destroying it. Technology is another application of science. Here they typically will use electronics of some sort as their examples. They have computers, catalytic converters, which convert the exhaust from automobiles to something less harmful, biodegradables. But it's not just technology like this. You know, the shovel is technology. At one time, it was very groundbreaking technology. Fire was a technology. The wheel was technology. So you can go back a long way and talk about technology, which are really just applications of science to make life easier for us. This is a list of some of the top chemicals that are produced in the US. The only one I'm going to discuss right now is sulfuric acid. It is also the most produced chemical in the world. It is so abundant in industry that the amount of sulfuric acid that is made and sold is a good indication of how the global economy is doing. There was a time that people weren't really sure whether air was matter or not. But one way to prove that it is that we can have the mass of a deflated balloon, let's say it was 5 grams, and then you inflated a balloon and now it's 6 grams after you've tied it off. And so we can assume that there must be matter in the balloon because the balloon's mass increased. This section of the chapter will begin to discuss matter. Matter, as a definition, has typically been anything that has mass and takes up space. I think a better definition is anything that has mass and volume. Mass is the amount of matter that an object has, whereas volume is how much three-dimensional space an object takes up. Atoms are the smallest unit that maintain a unique set of characteristics. If you break up an atom into protons, neutrons, and electrons, every proton is like every other proton. Every neutron is like every other neutron. Every electron is like every other electron. They don't really become unique with properties until you put them together. And so an element is a substance that can't be broken down into anything simpler and still have these unique properties. And then compounds are difficult to break down by physical means. They can be broken down by chemical means, but they are a joining of two or more atoms that have come together to make a new substance. This is an image of an atom, probably taken with an electron microscope. This is called a space-filling model. Space-filling models take these spheres, and atoms will typically abut and overlap. And so this shows atoms overlapping. These are actually a little bit closer to what we think the molecules would look like in person than the ball and stick model that you may be more familiar with. And here we have on the left a ball and stick model. Now this one is a diamond. And so carbon atoms in diamonds make bonds with all these surrounding carbon atoms. And if they were space-filling models, they would just be one kind of pyramid-looking shape with overlapping spheres. They would overlap much more like the diagram on the right. When we describe matter, we talk about the properties of matter. And so we can talk about physical and chemical properties. Physical properties are broken up into subcategories. Extensive properties are a type of physical property that do depend on the amount of matter that's present. So volume, mass, the amount of energy in a substance, these are all things that do take into account how much matter there is. Intensive properties, however, do not rely on how much matter you have. And it would be the same for any quantity of matter. The melting point, if you have a glacier's worth of frozen water versus one ice cube that you put into a glass, they're both the same material and they will both melt if they warm up to 0 degrees Celsius or 32 degrees Fahrenheit. If they get warmer than that, they melt. And it doesn't matter how much ice you have. Boiling points, densities, these are all the same. And this is a list of some properties of matter, about whether it can be conductive of heat or electricity and such. And so physical properties then are properties that we can observe or measure without changing what the material is. Physical changes can be changes in states of matter, melting and boiling and such. But ultimately, the identity of the material doesn't change. Water is still water, whether it's frozen or liquid or gas. And so here we have states of matter that they ask us to look at. Most people will talk about there being 3 or 4 states of matter: solids, liquids, gases, and sometimes, especially in some of the younger grades, they may or may not mention plasma. In solids, matter has a definite shape and a definite volume. In liquids, we have a definite volume, but we don't have a definite shape. So liquids can, to some degree, take the shape of the container. They don't fill the container automatically, but they do take the shape of the container that they're occupying. Gases will fill a container, and so they take both the shape of the container and the volume of the container. Plasma will do the same thing. Gases and plasma are actually very similar. Plasma is like you have a gas and you've given it so much energy that the electrons, some of them, start to come loose. We would find plasma in things like fluorescent light bulbs or bolts of lightning or stars. I should note here that there are actually more than 4 states of matter. Chemists have created lots of different states of matter. To be a state of matter, materials have to be in a certain state that has unique properties. And scientists have created some. There are some in nature that we've discovered. Neutrons are one of the parts of the nucleus of an atom. If you take away the protons, the neutrons can still come together to some extent through what's called the nuclear force, which will keep the nuclei of atoms together. and at a certain point, they attract from gravity, from gravitational forces. And so in deep space, people have discovered neutron stars. Neutron stars are amazingly dense. In a normal atom, you have a very tiny nucleus and a very large space that's occupied by electrons. And if another atom comes up and joins, they meet sort of at an outside edge, and the two nuclei are still very far apart from each other. But with a neutron star, you don't have all the empty space of the atom. It's just like two nuclei that would come together, but there are no protons. They're all just neutrons. And so these materials are incredibly dense. A spoonful of matter from a neutron star would weigh more than a mountain. This is a picture of liquid in the event you've never seen a liquid. But the more important thing here is that this is a graduated cylinder. And if you read a graduated cylinder, the top of the liquid will curve down slightly as the liquid tries to climb up the sides of the tube. And if you do a reading off of a graduated cylinder, you should always read it in the middle at the lowest point of that curve. This is just a slide that gives us some properties of gases. Here's plasma. They do show us a fluorescent light bulb and stars and lightning. Okay, this is water in 3 different states. When I talk about water on this diagram, I usually talk about Lego. With Lego bricks, if you have a box of Lego bricks and it's just loose bricks, it's like having water in the liquid state. They're all just sort of in there in a mishmash. If you pull some across, others are going to fall back into place. And so these Lego blocks that are just loose behave like a liquid with very, very large particles. Now, ice is a solid form of water, and so the ice always creates the same sort of pattern when it goes together. And this pattern has gaps in the middle that you can see in this left-hand diagram. Whereas the middle diagram doesn't really have very many gaps, or if they do have gaps, they're very small. But on the left-hand diagram, you can see that there are definite gaps. This is why when water freezes to become ice, the ice expands versus its state of matter when it's a liquid. It's why you don't put a bottle of water into your freezer, because the ice can expand and break the container. It also means that ice is less dense as a solid than it is as liquid water, which is a very unusual thing for most matter. Most matter becomes more dense as a solid than it is as a liquid. So because of this lesser density of solid water, it floats. And if you take your box of Lego and spill it on the floor, the particles are now very far apart, which is more reminiscent of a gas. In contrast to physical changes and physical properties, chemical properties are about how a material reacts, how likely something is to react, and if it does react, what happens to it? What does it become? Because part of the chemical change or chemical reaction is that you take a material and you change it into something else. This happens by the rearrangement of atoms. We don't take one atom and change it into a different kind of atom. That's actually a different type of chemistry. That's called nuclear chemistry. But chemical properties are just how likely is something to react? Is something going to burn? We would say it's flammable. It turns out we could also say something is inflammable. Normally you put in front of something to mean opposite, but flammable and inflammables histories as words were from different places, and they both came to mean the same thing. Go figure. This would be a chemical reaction that would have already happened, I think. So reactants are the materials that are about to change, and the products are the new things that you've made. And so on the diagram down here at the bottom for carbon and oxygen, those are the reactants, and the carbon dioxide is the product. The chemistry really happens inside of the arrow down here. And here are some examples of physical change. Electrolysis is a particular type of chemical reaction. If you take water and apply electricity to it, it will separate the water into hydrogen and oxygen. Normally, when hydrogen and oxygen undergo chemical reactions and change, they don't form hydrogen and oxygen like you might expect. Electrolysis will do that, but normal chemical reactions will actually just take one of the hydrogens away from H2O, and so you end up with hydrogen by itself and something called hydroxide. That's the O and the H that are left staying together. And so here's some lists of physical and chemical properties. So physical properties might be the color, they might be that an odorless gas was produced here. It might be that what it looks like when it's a solid. Chemical properties are more things like how likely is this to react? What temperature does this have to be before it starts to burn? This kind of thing. And so people tend to think about chemistry as the actual chemicals themselves changing and moving, but energy has to be involved. Energy is either absorbed or lost during chemical reactions. Here they tell us that about some of the different forms we can have for energy, heat, and light, and that's true. But it's never destroyed or just created from nothing. The law of conservation of energy tells us that we have to have the exact same amount of energy before a chemical reaction that we have after a chemical reaction. All right, so this slide shows us the difference between pure substances and mixtures. Pure substances are things that can't really be broken down by normal physical means. These include compounds and elements. Mixtures, however, can be separated by physical means. There are two categories of mixtures. One is homogeneous mixtures, in which the combinations are all kind of the same throughout. So it might be something like Kool-Aid, where one glass of Kool-Aid tastes just as sweet as any other glass of Kool-Aid because the sweetener is evenly mixed. Heterogeneous mixtures are unevenly mixed. And so these might be things like ice cream with mix-in ingredients, things like chocolate chip cookie dough ice cream. Milk would classify as a heterogeneous mixture because you actually can separate out, like from whole milk that comes from the cow, you actually can separate out milk and cream. They also have blood here, and blood can actually be separated out into the red blood cells and your plasma. And so here's another just very similar diagram. It just once again shows mixtures and pure substance. So mixtures have a combination of two or more different kinds of matter that are physically mixed. They're physically combined. They can be physically separated. And so homogeneous mixtures are also called solutions. If you have a solution of metals that you've melted and blended while they were liquids and then you let them cool and solidify again, those are called alloys. Heterogeneous mixtures are just heterogeneous mixtures. They are, however, not uniform throughout. It might be something more like Chex Mix. This is just different kinds of mixtures. On the homogeneous mixture on the left, you can't really pull any of that out. You can't really tell that it's mixed. On the right-hand side, where we've got, it looks like some sand, silicon dioxide is sand. We have some sand and some water, and the silicon dioxide will settle out, and you could separate these. So pure substances have fixed compositions. They are things like elements and compounds. They don't really have a good, easy way to separate them. They can be separated chemically, but they cannot be separated physically. This slide just has some different grades of chemical purity that you might see on packaging. All right, so here are some examples of homogeneous and heterogeneous mixtures. This slide is a list of means that we can use to separate mixtures. It is by no means an exhaustive list, but it's some very common methods that we can use to separate. The first one is filtration. This is according to size. So with a coffee filter, for instance, the pores in a coffee filter are small enough that the coffee grounds get stopped, but large enough that molecules of water can still go through. Density, if we have different materials that have different densities and they're in a mixture, the more dense material will go to the bottom, the less dense material will come to the top. Decanting is a very similar idea. It still relies on the densities of materials. This one has a density of liquids. Decanting is where if you have like oil and vinegar and they separate, the oil will float on top of the vinegar. If you wanted to separate these by decanting, you would very slowly pour the oil that's floating on top into a separate container, leaving the vinegar behind. Distillation is one way that we can purify water. If you have, say, salt water, and you boil the salt water, it's going to be separated by the different boiling points of the materials. Salt has a very high boiling point. You can take, we normally think of salt as being a solid, it's a crystal. It actually has a very high melting point. Anything that you can melt to a liquid, you can also boil to become a gas. However, the water that's in the salt water will melt and boil at much lower temperatures than the salt. So the boiling point of water being so low lets us boil the water away and leave the salt behind, and then we've separated a mixture of salt and water. A centrifuge is a device that spins materials and it can separate mixtures this way. The mixtures we separate by centrifuge tend to be liquids. Blood is one that we can centrifuge, and it can separate the blood cells from the plasma. If you've ever been to the fair and ridden one of the spinning rides, there's one that looks like a flying saucer. It's undergone a bunch of different names. There was one, it was a spaceship for a while, it was a cyclotron for a while, but it was like a UFO. You get in a couch that leans against the wall and it pushes you against the wall as it spins. The same force that you feel pushing against you there pushes against the more dense material in the mixture of blood more than it does against the lower density material. So the more dense material gets pushed to the bottom, the less dense material gets left at the top, and that's a separation method for materials like blood. Chromatography is something you might have done in a physical science class. In physical science classes, what they'll do is they will give you a marker that's got an ink in it that's soluble by probably water, and then you could mark on a piece of a coffee filter. If you put it in water, as the water moves through the coffee filter, it catches the ink. It gets to the ink and it carries some of the ink particles as the water travels. The real reasons are different charges and masses of the molecules of the dyes that are used in the ink. But what we see as people is we see the colors spread out. And so because it's got color in it, we call this one chromatography. Magnetism is a method. If you have iron filings and salt that you've mixed together, you can get the iron filings back out by stirring with a magnet. There's an experiment that you can do with iron-enriched foods, things like cereal. If you take cereal that's been iron fortified, something like Wheaties or multigrain Cheerios, and you crunch it up into powder, and then you make sort of a paste or a soup with it. If you have a strong enough magnet, you can put a magnet into it. Stir this mixture with a magnet, and when you pull the magnet out, it's got all this black powder on it. That's really the iron out of the cereal. When they iron fortify cereal, they really just, while it's still sort of a slurry, pour iron into it. So you could buy rusty cereal. I actually kept a bottle of Flintstone vitamins, and I kept it because they had been in the cabinet long enough that the vitamins had started to rust. So I kept them as a demonstration tool for class. The last one I've described here is solubility. Sometimes you'll get material where one substance will dissolve in a certain liquid and another won't. If we have salt and sand, if you want to separate it out, if you can you pour water into it, the salt will dissolve in the water, the sand won't, and then you can separate it out that way. And then if you might have to use another process, you might have to use like a filter to catch the sand, but let all the water go through, and then you've got one container with sand and one container with salt water, and when that salt water evaporates, then it will leave the salt behind. Evaporation is another possible separation of mixtures method that I did not list. And now we'll begin a discussion of the periodic table. This slide has the name and symbol of some elements. What we notice here is that the names and symbols don't really seem to match. And that's because the symbols were based on older names that have kind of fallen out of use for some of these elements. Copper, for instance, has Cu when you might expect Co, because the oldest name for copper was cuprum. Gold is very similar. Gold has Au because its original name was aurum. On the periodic table, this is a good one. It's color-coded. So what we'll find is that everything that's kind of red on this periodic table is a metal. And you'll see that most of the elements on the periodic table are metals. As we move from left to right, we see a band of orange, and these are metalloids. Metalloids are similar to metals, but not exactly like metals. And the green and the purple at the end are nonmetals. Even the noble gases are considered non-metals. And noble gases are in the right-hand column. They're the kind of purplish gray column there. They are noble gases because, much like human nobility, they don't mix with anyone else. They don't mix with the riffraff of the rest of the periodic table. The green ones are what we typically consider non-metals because they actually do get involved in chemical reactions. Noble gases normally do not get involved in chemical reactions. Hydrogen is on the left at the top. It's kind of an off-white. Hydrogen's unusual. It's sort of in its own little family up there. It is technically a non-metal, but it behaves like a metal sometimes. And if you freeze it until it's solid, hydrogen actually does become a silvery metal. The vertical columns, the up and down columns, are called either groups or families. They're called families because they have similar properties. The horizontal rows of the periodic table are called periods. If you get these backwards, just think about sentences. Sentences go left to right across the page and they end in a period. Horizontal rows go across the page and are called periods. So here are some properties of metals. Metals are elements that tend to be good conductors of heat, good conductors of electricity. They are, with only one or two exceptions, well, actually with only one notable exception, solids at room temperature. Mercury is a liquid, but that wouldn't be considered a general property of metals. They are malleable, so you can bend them or mash them out into sheets. Ductile means that you can make wire out of it. And we say that wires have tensile strength. And tensile strength means that if you pull on the wire is strong. And they've already mentioned that they conduct heat and electricity well. In the event you've never seen a metal, they do give you some examples of what a metal looks like here. So nonmetals are kind of just the opposite of metals in their properties. They are generally poor conductors. You'll find some gaseous nonmetals, some solid nonmetals, and even one liquid nonmetal. Bromine is a liquid at room temperature. They do tend to be kind of brittle. And like they said above, they are poor conductors. It is less likely that you've seen examples of pure nonmetals. So these are some examples. So the first one, carbon, it's very likely you've seen, if you've probably even eaten some if you've ever had meat that's been charred. Sulfur is this sort of yellow compound. It does have sort of a nasty smell when it mixes with hydrogen. There are different kinds of phosphorus. This particular one is red phosphorus. And iodine sometimes also looks kind of darker than that, but that's their example here. So metalloids share some properties of metals and some properties of nonmetals. They are conductive, but less conductive than metals and more conductive than nonmetals. Silicon is an example of a metalloid, and silicon is a material that's very important to us for use in computers. And as people get better and better at purifying silicon, computers have gotten faster and faster. We also mix a little bit of other material in with the silicon when we make computer chips to help the processing be faster. Noble gases are in the last family of the periodic table. That would be group 18. So altogether, there are 18 families as you go across the periodic table. These generally do not react with other elements. The ones closest to the top have never been used in making chemical compounds. The ones that are closer to the bottom, in a laboratory where you can create very unusual conditions, people have made compounds with those. It's not easy and it's not a common thing to do. They are all gases at room temperature. They do become heavier towards the bottom of the periodic table, and by the time you get down to radon at the bottom, radon is actually radioactive. All right, so this was the end of the notes for chapter 1. There is, however, a set of questions after this, so I'm going to just go through the questions here and we'll look at the answers. But this is the actual end of the notes for the first chapter. For the questions here, I'm just going to play the slide and then move to the next one. Each second slide will have the answer to the question that you are looking at.